Right. We continue with another application of flip-flops, registers. I introduced registers as a number of flip-flops which I use n number, n shift register. What is a register? It's n number of flip-flops used to store n bits of data information. That is what the register is. I'm going to give an example, and with that example, I will explain why these are called shift registers. At the same time, I will explain how do they store the data. Right. Suppose I want to store data of the form 1, 1, 1, 1. 4 bits. I want to store those 4 bits. How do I do it? Using registers. Since I want to store 4 bits, what it means, I will need 4 flip-flops. One flip-flop will store 1 bit of data. Easiest way to store this data, we have the D flip-flop. So you put out a cascade of D flip-flops. 1, 2, 3, 4. With my output, this becomes here, here, here. So we have D here. So this is D1, D0, D1, D2, D3. With it, I have Q3, Q2, Q1, Q0. A number of D flip-flops. All right, I have my clock positive triggered. My clock this means my circuit is synchronous. All right, how do I then demonstrate how I'm going to store my bits? 1, 1, 1. Best way I can demonstrate is this will become my output. This shift register is called a serial in, serial out shift register. And I just chose this one to explain application of the D flip-flops. How do we apply the D flip-flops? All right. Suppose I have my clock, then I have my outputs, Q3, Q2, Q1, outputs of each flip-flop. Initially, I have my outputs as 0, 0, 0, 0. The outputs initially. What will be my next state when I hit the positive edge? What will be my next state when I hit the positive edge? All right. My next state when I hit the positive edge, I want to store 111. This is my MSB, most significant bit, my LSB, my least significant bit. What I do, I feed in the least significant bit first into D in here. Then I feed this. Then this will follow. Then this will follow. It will follow sequentially. And this is how it is done. All right. If I feed my 1, it means the next state change, Q3, will change to 1. Why? Because when D3 is close to 1, according to the truth table of the D flip-flop, 0, 1, 0, 1. When D is close to 0, Q becomes 0. D is close to 1, Q becomes 1. So if I feed in a 1 here, my LSB, it means my D3 will become a 1. And when the clock is positively triggered, my Q3 will change to be a 1. But what happens to my Q2, Q1, Q0? These things are happening at the same time. So when the clock hits here, it also hits here, it also hits here, it also hits here. I've said when it hit here, my Q3 changes to 1. But before here, I had a 0. And this 0 is moved to be the input of D2. When I have a 0 here, my output will be a 0. The 0 which was here moves to D1. I have a 0 here. It means my output will be a 0. So I have something like this. Q2 is 0, 0, 0. When I input my first bit, the LSB, right, D0, you have Q1, D1. When I input my LSB, 1, when the clock triggers a change happens in this flip-flop at the same time. This one, and this one. Now what happens? This output goes into D2. This goes into D1. This goes into D0. So we have something like this. Q3 goes into D2 and it triggers a change on Q2. Q2 goes into D1 and triggers a change on D1 on Q1. This goes here. When I hit the next clock change, it means my input again is a 1. And now what happens? Here, this one moves here. We now have a 1 as output because when D2 is equals to 1, because of this Q3 is now equal to 1, we have an output Q2 which is equal to 1. This now goes here, 0. This now goes here. We have another 0. When another step change comes, another 1 is fed in here. And this one goes here. This one goes here. Everything is happening sequentially at the same time. When another clock hits, I have 1, 1, 1, 1. So this goes here, this goes here, this goes here. Those arrows demonstrate why this one is called a shift register. Because you can see something is shifting there. Those zeros, ones, they're shifting. Now at the end, what do we have is our outputs in the D flip-flop. We have 1, 1, 1, 1. Then we stop. If we want to store 1, 1, 1, we stop there. And it means we have stored the bits of information 1, 1, 1. This can be demonstrated as well by using a clock. I'm hoping this can be the best demonstration. By using a clock, we have how many? 5. 1, 2, 3, 4, 5. The last one. Okay. This is my clock of that same circuit. I have Q3 initially 0. Q2 initially 0. Q1 initially 0. and Q0 initially 0. Positively triggered. This is a positively triggered clock. So it means when I go from 0 to 1, there is a state change. Right. I begin with Q3. When I hit the first state change, that's the same time I input my LSB 1 here. It means the state changes to 1. Why? Because for the truth table of the D flip-flop, I have D and Q plus 0, 0, 1, 1. When D is equals to 1, the next state will be 1. So this will be my next state until there is another state change. Here, when the clock is 0, we have the memory state. It means my 1 is kept like this. All right. Now, what happens when the second state change comes? When the second state change comes, my Q3, another 1 is fed in. Mute yourselves, please. Another 1 is fed in. So here, this 1 remains. When the next state change comes in, this is for Q3. Another 1 is fed in. So it remains a 1. Now we have 3 1s. Another state change, another 1 is fed in. It remains a 1 throughout. Now to my Q2. The first state change. The first state change, my Q2 remains a 0. Why? Because it all depends on the input of Q3 here. So for the first state change, my Q2 is a 0. When the clock is equal to 0 at this point, this memory state, it remains a 0. Now, when the next state change triggers, my D2 is now equal to Q3, which is equal to 1 at this point. It means my Q2 will change to 1. And it continues. If I use the same logic I used up there, it continues until the end. For this one, Q1 will depend on this output. Because for me to get Q1, it depends on D1. D1 depends on Q2. So if Q2 is low, D1 is low. If D1 is low, it means my output is also low. So next state change here, I began with 0. Next state change, D is goes to 0. I have a 0 here. In the memory, it remains. Next state change, my Q2 was 0 still here. So I have a 0 in the memory here. Next state change, my Q2 now at this point is 1. So it means this changes to 1. Same logic up until the end. I apply that same logic to Q0. I will have something like this. Only at this state change will I get a 1. So I have something like this. So what do I have? I have my shift register storing the 1 bits at this point. If I do this is 0, 0, 0, 0. Right? Put that. Then next state change, what do I have? I have 1, 0, 0, 0. The next state change, this is 1, this is 1, this is 0, 0. Then this change, I have 1, 1, 1 here, 0. And lastly, I have 1, 1, 1, 1. And it means I've stored this set of bits after how many changes? After 1, 2, 3, 4 changes. I've stored 1, 1, 1, 1. In telecommunications, I can apply this. in an example of a parallel in, multiplexing, parallel in, serial out. What it means for parallel in, serial out. Let me do this. Let me just change here. Parallel in, parallel out. It means I have, now instead of having this serial input, only one input, I can have this as an input, this as an input on its own, this is an input on its own, this is an input on its own. Parallel in, I have input, let's say this is not D, okay, let's say D3, D2, D1. This is parallel in, I'll have a serial out. What does this mean in telecommunications? It means I can send data here, multiplexing, voice, I can send internet, text, image. They are all joined in to form one output. And they are then transferred over the transmission line. So if I have my transmitter here, having 4 parallel data inputs, I apply the shift register, parallel in, serial out. What will happen? I can only use one transmission line to send 4 inputs of data instead of having 4. Instead of having 4 transmission lines, if I apply this parallel in, serial out, it means I can eliminate this, and this data can be sent using one transmission line. Transmission line. Application of the flip-flops. This is a typical exam question. Parallel in, serial out. How can I apply flip-flops to have this type of register? How will it work? Examples of how it works. Where will it work? Transmission lines, perfect example. It multiplexes a signal. It's not only this which multiplexes a signal. This is a multiplexer. We also have this parallel in, serial out, multiplexing a number of different inputs. Application of flip-flops in registers. There are many. We also have here, I think we have parallel in, parallel out. Does that exist? I'm hoping it exists. Parallel in, parallel out. Let me see.
It exists.
It exists. Serial in, serial out, parallel in, parallel out, parallel in,
Also,
serial out. What else?
Serial in, parallel out.
Parallel out. Application remains almost the same. All right, so I was saying application, how do you apply the flip-flops remains almost the same in all these registers. So I've just gave you an example of how I can apply flip-flops here. Using that same logic, you can apply it here, here, and here. And I will leave that to you. One of these is definitely in the exam. One of these is definitely in the exam. All right. Another application. We have application in counters. So we've talked of the frequency divider. We've talked of registers. Now we talk of counters. I want to count 0, 1, 2, 3, 4, 5. I think a lot of applications which comes with counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, a decade counter. How do you do that? Using a flip-flop. All right. So I have the definition. A counter is a digital circuit used for counting pulses. We all know what a counter is. We have two types, repo, asynchronous. Two types of counters. We have asynchronous or these are also called repo counters. We also have synchronous counters. These ways, the only difference between these two, one is a clock, one doesn't have a clock. Definition, asynchronous, no clock. Synchronous, clock. Very simple definition. 2 marks zemahara ipapap. You see munaj foira, and you wonder how. Right. We start with the asynchronous, the repo. I'll give an example. Asynchronous of a counter which counts 0, 1, 2, 3. Back to 0, 1, 2, 3. This is a typical repo counter. So we have something like this. I need the space. I need the space. So this is a asynchronous. Asynchronous counter. So for this one, I'm going to use the T flip-flop. So there we have our T flip-flop. So this is my QB. Let's say this is my QA. So this is flip-flop A, flip-flop B. It's a T flip-flop. So I have TA, TB. Right. So this is the same. These inputs are the same. Then the clock here negatively triggered and is equal to the output QA. I have another clock negatively triggered here. This one is not, there is a clock, yes, but the clock is not synchronized. For a synchronized clock, we would have had something like this. Being the input there. Now the circuit is synchronized. But as I look at it like this is not a synchronized circuit, a synchronous counter. All right. How does this function? Out. I will explain this using this, my clock, my QA. Let me put my QB, my QA, state changes. I think this is called the state change table or something like that. This is my output, state changes. Initial state. And my state changes occur only when there is a negative edge trigger because of this. All right, initially, let's say my outputs were 0, 0. And that means my decimal output is 0. decimal 0, 1, 2. That is decimal output. What will happen if there is a state change? If this negative edge triggers a state change, what happens? Right. Truth table knowledge of the T flip-flop will be required here. I have T, I have Q next. At least I have clock. When the clock is 0, whatever T is, what do I have here? This should come up easily, by the way. This never changes. When the clock is 0, this never changes. Practice. With practice, it will come out easily. Then if the clock is 1, I have 0, I have 1. When T is equals to 0, what do I have? Do help me, please. The T flip-flop is a modification of the JK. For my JK, if J is equals to 0, K is equals to 0, what do I have?
1.
1, are you sure? I also have the memory state. I said if J is equals to K is equals to 0. If S is equals to R is equals to 0. If clock is equals to 0. If D, nope, not D. If T is equals to 0. All these are the memory states. With practice, you understand the whole meaning of this. Let's say you haven't practiced enough. You will have probably 3 weeks to practice before the exam. When T is equals to 1, for the T flip-flop, what do we have? T flip-flop. We have the toggling state. We have the toggling state. Now, what happens to my next state? This is my present. This is 1. It's always in the toggling state. All right? My T flip-flops are always in the toggling state as they are. Now look what happens. For my next state change, I'm at QA is equals to 0. What happens to the next state of QA? I have 1 here. What will happen is toggling. It means 0 changes to 1. What will happen to my, running out of time, what will happen to my QB? My QB is determined by this clock. That clock is determined by QA. The transition of QA is from 0 to 1. If I transition from 0 to 1, what is this? This is a positive trigger. But since my clock should be a negative trigger, it means no change happens for QB. So QB remains the same. What do I have as my decimal output? It's a 1. As I continue, you probably understand this more. What will be my next state change when the trigger comes? QA, T is equals to 1, toggling. It means my QA will change to a 0. When my QA changes to a 0, the change is from 1 to a 0. 1 to a 0. This is a negative edge trigger. Since my QB depends on this clock, which depends on QA, in this case, which is negative triggered, it means this is equal to 1. There is a negative trigger here. There will be toggling as well. When there is toggling here, I go from 0 to 1. What do I have as my decimal output? A 2. For another negative H trigger, here toggling as usual. For this flip-flop, it's always toggling because the clock is always negative triggered. But what happens here? What happens here, I'm moving from 0 to 1. This is the positive edge trigger. It means nothing will happen. Why nothing will happen is because my clock here is a negative. So during changes from 0 to 1, nothing happens. So it means I have a 1, 1 here, and this is a 3. Another state change. What will happen to this one? A, toggling. A is always in the toggling state. It will toggle to 0. What will happen to QB? I look at QA. State transition from 1 to 0, negative H. Negative H triggers a state change here. It means this now is in toggling state. 1 changes to 0. I'm back to 0. Then I continue 1, 2, 3, 4. 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. And right there we have our counter. Application of flip-flops in counters. Asynchronous counter. 6 minutes. Questions, comments. I think I'll have one last session, very small, to finish up everything. Any questions here?
No, Bunza.
Yes.
But asynchronous means there is no control clock.
Yes.
In this case, when the clock changes, isn't it that clock will control?
But is it synchronized for all the flip-flops? Let me put that like this. If I have one flip-flop and there's a clock, let's say this is a D flip-flop. This is a synchronized flip-flop. There is a clock there. This is synchronized. One flip-flop. For one flip-flop, I can have this as well without a clock. This is asynchronous. So this is sync. This is async. But now when we have multiple, D, watch, Q, Q bar, Q, Q bar, D, another clock, another clock. This is my clock. This is my output. Look what is happening here. This is a synchronized circuit. Why? Because when this clock is 1, at this point it is also 1. It means change here, there's a change here. This is synchro. Nice. It's different if I have something like this. It's different now if I have something like this. There is a clock, yes. But the clock is not synchronized. In this case, my clock is not synchronized. What do I mean? When here is equal to 1, are you guaranteed you have a 1 on this clock?
Okay,
but my bad. Probably when I introduced asynchronous and synchronous, it only applied to one flip-flop. But now when you have many flip-flops, the no clock definition now doesn't sound okay. It now doesn't sound okay. Now there's an element of synchronization. Are all the flip-flops synchronized? If not, then we have an asynchronous circuit. Thank you very much for posing that question. I think it clears a lot of things. Any other question, comments? Now, what you need to do as a student of logic design, apply the same logic for a decade count research. How do I make a decade count? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9,